last class we have seen so far that we have done this formula, that is the quantity of heat transferred to a substance is given by Q equals ms delta T. In the question we had done, we talked about we found out the specific heat of the substance. I talked about the water equivalent also. Is that okay? What is water equivalent? Do you recall that?
Mass of water to heat capacity is same.
Yes, mass of water which has the same heat capacity as the given calorimeter. That's right. So, let's consider this question. I've got three different liquids, A, B and C, having a temperature 10, 20 and 30 degrees centigrade. When we mix A and B, we get, when we mix equal masses of A and B, we get 18 degrees centigrade as the temperature of the mixture. When I mix equal masses of B and C, I get 25 degrees centigrade as the temperature of the mixture. So what will be the temperature if I mix equal masses of A and C? Okay, we are not talking about if you mix B and C you get 25, if you mix A and B 18, if you mix A and C what would you get? That's the question. Yeah, are you in 22? I don't think it's 22. Yeah, B and C is 25. Yeah, you get 26, right? 26 degrees centigrade. Basic idea we are using is heat loss equals heat gain. That's the principle we are using. So if you're talking about, let us say in the first case, when you're talking about A and B, so who is losing heat and who is gaining heat? If you talk about A will be losing heat, M 20 minus 18 will be equal to MSA 18 minus 10. This is the temperature difference, and this tells you that masses are cancelled. 2SB equals 8SA or SB equals 4SA. This is the first equation you have got. Similarly, we can do it for this also. For this one we can say heat is lost by C. MSC 30 minus 25 will be equal to heat gained by B will be 25 minus 20. So we notice that basically SC equals SB. In other words, this is equal to SC. That is the equation we get. This is the relation we have got. SB equals 4SA equal to SC. Now the same thing now we employ here. So this final temperature will be something, let us say T. We don't know how much it is, but surely it will be between 10 and 30. So C is going to lose the heat. So we can say MSC 30 minus T is equal to MSA T minus 10. So you solve this and get your T. Yeah, is that okay? We know the relation. What is SC by SA? We know SC by SA is 4. You can say SC equals 4 SA, substitute and get your result. So the T that you get here is 26 degree centigrade. Yeah, this is the basic principle of calorimetry which we are using here. Heat lost equals heat gained. Yeah, is that okay? The first part. Now, I pose a second question on this. The second question is, if equal masses of all the three liquids are put together, what will be the temperature of the final mixture? What is the final temperature of the mixture if equal masses of all the three are put together? I'm saying it in a different manner. What we say is heat loss equal to heat gain can also be expressed as in an integer sense like this, that sigma Q system equals 0. If you are considering A, B, C as part of a single system, and here we are also neglecting, if you are doing it in the calorimeter, we are neglecting the water heat from the calorimeter. We are assuming as if there is no loss of heat to the vessel. That's the assumption here. So in this case, if you do it like this, then you will say that this is equal to MSA. Let us say final temperature is T. So always the heat will be T minus 10 plus MSB T minus 20 plus MSC T minus 30 equal to 0. We write like that. Now this is like taking up an integer kind of a sense. If temperature is more than 20, this will be positive. If this temperature will surely be less than 30. So this will be negative. At least one of them will be negative. So you can solve this and get your answer. So get your answer. SA, SB, SC, you know the relation among them.
23.3.
That's right. 23.3 degrees centigrade. That's the final temperature of the mixture. So what you basically saw is you can this and saying heat gain equal to heat lost are equal. If you're mixing up more than one, then more than two, then this kind of a system would be useful for us. Yeah, are we through with this question? The next question. A piece of metal, or let us say a piece of insulated metal, is heated with a constant source of electrical power P. So by saying this is insulated, I mean that whatever heat goes to the metal is only in the metal. There is no leakage of heat from the metal. It is seen that the temperature of the metal varies as alpha T power 1 by 4 plus T naught. T is the time and capital T is the temperature. Alpha and T naught are constants greater than 0. So you got to find out what is the heat capacity of the metal. You will express your answer in terms of as a function of power and temperature. You got to find the heat capacity. Mass into specific heat is heat capacity. What is the see the very fact that this heat capacity is not a constant. It's a function of power as well as temperature. So far the heat capacity you're talking about has been a constant. This suddenly won't be a constant. So what is your heat capacity equal to? When you give a certain heat to the metal, I can say like this, Q equals ms delta T. See, delta T means what? By the way, what is the initial temperature of the metal?
T naught.
T naught. So when you give a quantity of heat Q, the temperature of the metal goes up by something. This is how it is going to behave, MST minus T naught. But if this thing is a variable, this is the equation in assuming this is constant. If it is not constant, then we will say like this. This is a more accurate equation. Okay, that's like saying velocity is ds by dt rather than saying it is s by t. This is the elemental notation more accurate. So this is more accurate than that. When you integrate this, you will get that. So we'll say like this. And what is it that you want to find out? You want to find out this. This is your target unknown. This is the heat capacity. And what is power? If I differentiate both sides by time, small t is time, capital T is temperature. The amount of heat supplied is nothing but, this is the power. We have to find out this. This you can find out by, this function is given to you. So you can differentiate this function, get what is dt by dt. dt by dt is what? Differentiate this. Yeah, is that okay? And this you can further write in terms of, I don't want the final answer in terms of time, so substitute back. What is it in terms of time? This will be.
That's what I said the same thing, so I just used time as T as time, not temperature. That's what.
I heard your T as the capital T because I have told you give me the answer in power and temperature.
I didn't read that part. That's why.
Okay. So now if you substitute it there, you get the required answer. You get ms equals, yes. Final answer, can you give it to me now in the appropriate form? 4p t minus t naught the whole cube.
Yeah, upon alpha to the power 4.
Upon alpha to the power 4. That's right.
Yes.
So that's it. So we move on to the next idea in calorimetry, namely that of latent heat. See, whenever you are moving from a liquid phase to a solid phase, or from a solid phase to a liquid phase, during the transition, this will happen at melting point, this will happen at the boiling point, we give the heat required by this formula Q equals ml. The heat is used up in breaking the bonds. Now here, this we call as latent heat of vaporization, this we call as latent heat of fusion. So it is as if that when you just cross over, there is no change in temperature here. When you come to the next phase, if you are moving from liquid to higher temperature of liquid, then there is a change of phase, change of temperature. When you are going from solid to liquid, for example, 0 degree ice, if it melts to 0 degree water, you require Q equals mLF. I can give you the values. For ice, the latent heat of fusion is given by 80 calorie per gram. Similarly, for steam, the latent heat of vaporization is about 540 calorie per gram. Can you explain why does water in an earthen pot become cold? मटके का पानी ठंडा क्यों होता है? Basically, cooling effect. Why does it happen? Is what I am asking.
Sir, the high energy particles move away evaporate from the surface of the pot, and it lowers the temperature inside the pot.
Because it takes the heat from the water.
Okay, that's right. The porous pot kind of absorbs the water, and some amount of water kind of evaporates. Each gram of water which evaporates takes away with it 80 calories. You do lose some water from the pot, but rest of the pot becomes cold. That's the idea.
So you said 80 instead of 540. The vaporization.
I'm sorry. Yeah, this is it. Each gram, yes, it is better than that. Each gram takes 540 calories from it, and the rest of the part loses that heat, and that's how it becomes cold. This is the basic principle of refrigeration. Even in the refrigerator that we use, the same thing happens. Only then we are using freon gas as the evaporant, the coolant. The freon gas evaporates. If you see especially the ice box of a fridge, you will find some fine tubes passing around it. Those tubes are containing freon which is expanding, and they kind of absorb the heat from the refrigerator environment. But here we don't allow the freon to escape. What we do is the gas is there, and there is a compressor in the fridge. We kind of press it, the gas becomes liquefied, and again the cycle is repeated. So refrigeration cycle goes on repeating. But the main idea of cooling is this only, that Q equals mLV. Yeah. If you have, suppose you have a cold drink where ice is floating, means it is 0 degree centigrade. You take a sip of that, and maybe you can have an ice cream from the other hand, and you put a scoop of the ice cream in your mouth. Now, which one do you feel colder? Let's say ice cream is 0 degree centigrade and the drink is also 0 degree centigrade, but your experience tells you what? Do you feel the same temperature?
Ice cream.
You will feel the ice cream colder. Why?
In liquid state, when it transforms from a solid to liquid, it has latent heat.
Exactly. So each gram, suppose 1 gram of ice cream is there. Let us forget about the cream part. Let us say the ice part. 1 gram of ice from 0 to 0 degree centigrade of water will take away 80 calories from your mouth.
Yeah.
Then it will come to the body temperature. What is the body temperature?
25.
37. So ice cream will the water which has melted will come from 0 to 37 in your mouth. So it's going to absorb 80 plus 37, 117 calories for every gram which melts. Whereas if you take a sip of the cold drink, it is already in the liquid form. It will come from 0 to 37, it only takes 37. The ice cream takes 117 and this takes 37. So you can see almost 3 times. So ice cream is much colder. That's why we call it an ice cream, and we prefer ice cream because it's much colder than just the liquid part. The same thing is said for in industries where they use heated steam, etc. Sometimes leaks happen and very great fatalities can happen. Steam burns are much more severe than hot water burns. Again, why? Answer that. So every gram of steam that condenses is going to pour more V's. 540 calorie per gram is going to be put, other than whatever extra steam heat is going to be put. That's right. So Q equal to ml, that is the idea. So here, let us see some questions. I'm going to give you a series of questions. They are like related. Slight changes, and that will become the next question to give you the idea. Let us see. you have got an insulated vessel, whereby I mean that the vessel does not take away any heat. So we don't bother about the heat taken away by the vessel, so that has been removed from the question. So I'm going to talk about different cases. Let us say case 1. Case 1, you have 250 gram of water at, 250 gram of ice at 0 degree centigrade and 600 gram of water at 18 degree centigrade. You have to find out what is the final temperature of the mix and what is the composition of the mixture. I mean, what does it contain? Water, ice, or ice-water combination. And these are the values given to you. The values given to you is latent heat of fusion for ice is 80 calorie per gram. The specific heat of water is 1 calorie per gram per degree centigrade. The specific heat for ice is 0.5 calorie per gram per degree centigrade. So you can use these given values and solve this question. Now to deal with such questions, I'm saying we'll use this kind of a diagram which I'm calling as a if diagram. We're going to basically budget the heat. So you might, think of it like this. If you are, first of all, let us draw the 0 degree centigrade, that is the melting point which comes into place. If there is a boiling point and melting point, bring that in. And then write the temperatures which you have for the different components. You have this at 18 degrees centigrade. So these are the only two things which play a role here. Now here you have how many grams of water? 600 gram of water, and you have 250 gram of ice. Now we do not know what is going to happen. What all can happen? Maybe all the water will come to 0, or maybe all the ice will melt, or maybe both of them will go to some temperature at the top. Now any of these things can happen depending upon the amount of water and ice available. So what we do is, first of all, say like, so I'm not saying this is going to happen, we are saying an if. What if all the water comes to 0? Now this is, I'm not saying it does happen, I'm saying that's why I'm calling it an if diagram. What if this happens? So what if this happens? How much heat will be given by water?
10800 calories.
600 into 1 into 18 ms delta T. That's right. So 18 6 are 108. So 10,000. Yeah, you got this part. I'm saying what if 600 gram of water comes to 0? So the amount of heat release will be ms delta T, so it will be 10,800 calories. Is that okay? Now here